Hi, I'm Mark Barsamian. In this video, I will introduce what's called the fundamental theorem of calculus, and then do a number of examples involving using the fundamental theorem of calculus to find definite integrals. This material is from section 5.5 of the book. More specifically, the first few pages of that section, examples 1 and 2, are relevant to what we're doing in this video. The corresponding homework is this fairly large collection of exercises from section 5.5. Recall the definition of the definite integral from section 5.4 of the book and from a previous video. The definite integral of f of x from a to b is denoted by this symbol. Remember that the definite integral can also be called the signed area of the region between the graph of f and the x-axis on the interval ab. And the official mathematical definition is this. The signed area, that definite integral, is defined to be this limit, the limit of the left sums with n subintervals as n goes to infinity, which is also equal to this limit, the limit of the right sums, the right Riemann sums, with n subintervals as n goes to infinity. There's some additional terminology that I neglected to include when I introduced the definite integral in a previous video. The number a is called the lower limit of the integration. The number b is called the upper limit of the integration. Recall that in a previous video we used rectangles to estimate the signed area of a region. The region was between the graph of f of x equals 5 plus x squared over 10 from x equals 2 to x equals 12. So this blue shaded region. And that signed area is denoted by this definite integral symbol. Because the function f of x is increasing on the interval from 2 to 12, we know that we have this, what I call, area sandwich. The area of this green region, which is made up of a bunch of rectangles, is less than the area of that blue region. And the area of the blue region is less than the area of this red region, which is made up of a bunch of rectangles. And the area of those green and red regions are denoted by these symbols, and they're called the left sum and the right sum, the left Riemann sum and the right Riemann sum. And recall that in previous videos we computed values of the left Riemann sums and the right Riemann sums. For the picture on the previous page, the values were the left sum was 94, the right sum was 122. Those were the left and right sums with 5 subintervals. So that gave us lower and upper bounds on this unknown signed area. And then we used a computer to find the left sums and right sums with more and more subintervals, more and more rectangles, all the way up to 10,000. And based on that area sandwich, knowing that the unknown signed area had to be between this number and this number, we made a guess, an estimate, that unknown blue area was probably around 107.33. Now note that we've only seen that one example of the definition of signed area, the definite integral, in use. That is the definition that says that this definite integral, that signed area, is a limit of Riemann sums. And in that example, we used a computer to find ln and rn for particular values of n as n got larger and larger. And we guessed at a rough value for the limit. That is, we guessed at a rough value for the value of the definite integral. So in a previous video, we discussed these obvious questions. Can we do those sums analytically, obtaining general formulas instead of having to do repeated calculations of y values? And the answer was yes. It is possible, but not at the level of Math 1350. The math involved in obtaining those formulas is above the level of this course. And another question was, if we had those formulas, could we find this limit analytically without having to use a computer to find ln and rn for larger and larger values of n, like we did in that table above? The answer to that was yes. If we had the general formula for the value of a particular Riemann sum, ln or rn, then it would be possible to find the limit using our limit laws. But the holdup here is that obtaining those formulas for the Riemann sums, ln and rn, is above the level of this course. So we're stuck with this situation. We would like to be able to compute the value of definite integrals using analytic techniques at the level of our course. The question was, is there an easier way to compute definite integrals analytically? That is, for a general function f of x, whose graph is not made up of basic geometric shapes, we want an analytic way to find this signed area, the definite integral, which officially is defined as this limit of Riemann sums and also this limit of Riemann sums. So the question is, what do we do? Is there another way, an easier way, to find this value of the signed area? That brings us to section 5.5, the fundamental theorem of calculus. I want to start our discussion for this section of the book by recalling notation that we've used for integrals. We've seen two uses of the integration symbol. One use of the symbol was the indefinite integral, this symbol, and that symbol denotes the general antiderivative of f of x. Another use of the integration symbol is this symbol, the definite integral of f from a to b. And what that means is the signed area of the region between the graph of f of x and the x-axis on the interval from a to b. The two concepts, antiderivative and signed area, seem unrelated. It should seem strange that such similar-looking symbols would be used to denote such dissimilar mathematical concepts. But it turns out that there's a very important relationship between the two concepts. The relationship is called the fundamental theorem of calculus. So the fundamental theorem of calculus is about the relationship between definite integrals and antiderivatives. It says this: if a function f of x is continuous on an interval a comma b, and capital F of x is an antiderivative of little f of x, then this definite integral is equal to this expression. Now we should carefully read the symbols of the fundamental theorem to fully understand what it says. What it's telling us is that given a function f of x that's continuous on an interval ab, there are two processes that one could run to get a number. Process one that leads to a number is to use the definite integral. We'll define the result of process one to be the number. That's the signed area, which is also called the definite integral and denoted by that integral symbol. Now, as we've discussed, we have a definition of what this signed area means, a definition of how to get its value using a limit of a Riemann sum, but we have no practical way to compute that value analytically using Math 1350 level skills. Using Math 1350 level skills, we can only get the signed area analytically in certain simple cases when the graph of f is made up of basic geometric shapes. So process number one results in this number, that is the definite integral. Process two that leads to a number involves using the indefinite integral. The indefinite integral can be used to find an antiderivative of little f of x. That antiderivative is a function that could be called capital F of x. So this function form is the indefinite integral. Then one substitutes the endpoints of the interval into capital F of x to get two numbers, capital F of a and capital F of b. And then we define the result of process number 2 to be this number, capital F of b minus capital F of a. That number is the result of process number 2. So process number 1 was to use the definite integral to get a number. Process number 2 was to use the indefinite integral to get a number. The fundamental theorem of calculus says the results of those two processes are equal. The usefulness of this fundamental theorem is that it answers the question posed at the beginning of the video. That is, we're often interested in the number that's the result of process 1 because it represents a signed area that we want to find. But we generally have no way of finding that number analytically because it would involve difficult techniques that are beyond the level of this course. But process number 2 is straightforward. We can use our indefinite integral rules to find an antiderivative, capital F of x, and then substitute in x equals a and x equals b to get two numbers, capital F of a and capital F of b, and then subtract to get this number, capital F of b minus capital F of a. The fundamental theorem tells us that the number that we get from process number 2 equals the number that would be obtained from process number 1. Our first test of the fundamental theorem will be to use it on a function where we actually do know how to find the number from process number 1. That is, a function for which we know how to find the signed area using geometry. Example 1. The goal is to find the value of this definite integral using two methods. Question A will find the definite integral by using process number 1. That is, we'll interpret the definite integral as a signed area and just use geometry to find that area. So to do that, we draw the graph of little f of x equals 2x minus 4 from x equals 0 to x equals 6, and then we shade the region between the graph of f and the x-axis on the interval from 1 to 5. The shaded region is made up of two right triangles. The red triangle has a base of 1 and a height of 2. Its area will be computed using the formula for the area of a right triangle. Area is 1/2 the base times the height. We end up getting the number 1 for the area of that red triangle. The green triangle has base of 3 and height equals 6. So using the right triangle area formula, we find that its area is 9. So the signed area is minus the red area plus the green area, which gives us a signed area that's the number 8. So using geometry, we're able to compute this definite integral and find the value 8. That's the result of process 1. Now we'll find the definite integral using process number 2. That is, we'll find the indefinite integral by integrating, and then we'll compute this value. So first we find the indefinite integral. Now remember that it's helpful before finding an indefinite integral to rewrite the integrand. The reason that's helpful is that it's written now as two terms that each have a constant times a power function. That means that when we find the indefinite integral, we can use the sum and constant multiple rule to break this up into two separate integrals, and in each integral, pull the constant multiple through the integration symbol and leave the power function inside the integral symbol. Now this left integral has a power function with n equals 1. The right integral has a power function with n equals 0. Because remember that the number 1 is x to the 0. So now we integrate using the power rule, and the result is that the indefinite integral is x squared minus 4x plus c. Notice that the indefinite integral is a function form, and so it has a constant of integration. Now we find this quantity, capital F parentheses 5 minus capital F parentheses 1. Well, that just involves substituting x equals 5 and x equals 1 into this formula for capital F of x. The result is a bunch of arithmetic that leads to the number 8. So the result is that this expression is a number, and it does not contain any unknown constants. When we start this calculation, we have a constant of integration plus c. But notice that there's a minus sign that results in this plus c canceling that plus c. So the final result does not contain a constant of integration. Now, compare the results of A and B. In question A, using geometry, we found that the definite integral was 8. In question B, using process number 2 involving the antiderivative, we found that this quantity was 8. The results of those two processes are equal, as predicted by the fundamental theorem of calculus. So our first example was a success. It confirmed what the fundamental theorem of calculus says, that the two numbers obtained by these processes are equal. The number obtained that's the result of process 1, that definite integral, is equal to the number that's obtained by the result of process number 2, this computation involving the antiderivative or the general antiderivative. But remember, the importance of the fundamental theorem of calculus is that for many functions, process number 1 is not possible using Math 1350 level skills, while process number 2 is possible. Later in this video, we'll consider more examples where the fundamental theorem of calculus is used. But before doing that, it's useful to introduce some new notation. What I call evaluated at notation is this symbol, a function with a vertical bar next to it, and at the base of that vertical bar, kind of as a subscript, is a symbol. This is spoken capital F evaluated at A. What it means is the number capital F parentheses A. So this symbol just simply means the number that results when you substitute that number into this function. So for example, if we let capital F of x be this function, the question is find this, capital F of x vertical bar with the subscript 2. That's spoken capital F evaluated at 2. Well, what that means is, again, we just simply replace that symbol with this symbol. That is, we substitute 2 into the function capital F of x. Well, that just involves a bunch of arithmetic. And the result is this circled expression. So capital F evaluated at 2, that symbol, equals this expression. Another notation that's useful is what I call the change in f notation. It's denoted this way. A function with a vertical bar next to it, and at the top and bottom of that vertical bar on the right side are two numbers. This is spoken the change in f from a to b. And what it means is this number. You substitute b into f, you substitute a into f, and you subtract to get a number. So for example, let's again let capital F of x be this function. Find this. Well, that means to substitute 12 into capital F and substitute 2 into capital F and subtract. Well, that's just a bunch of ugly math, just substituting numbers into that expression and grinding out the result using arithmetic. With careful calculation, we end up with this, 322 over 3. So this symbol denotes this calculation, which results in this number. Now I'd like to use that notation, that change in f notation, to rewrite the fundamental theorem of calculus. remember that the right side of the fundamental theorem of calculus is this expression, capital F of B minus capital F of A. We see now that we can use the change in F notation to write that in this way, the change in capital F from A to B. Well, we can use that to rewrite the fundamental theorem of calculus. We rewrite the right side of the fundamental theorem of calculus using change in capital F notation. But now we realize also that capital F, that general antiderivative, is obtained by doing an indefinite integral. So the result is that we have the fundamental theorem of calculus written in this new way. On the left side, we have an indefinite integral, and on the right side, we have this expression involving an indefinite integral. This new way of writing the fundamental theorem of calculus is so useful that it's worth presenting it in a nice green box. So here is my way of thinking of the fundamental theorem of calculus. Again, it's a relationship between definite integrals and antiderivatives. The fundamental theorem says if a function little f of x is continuous on an interval a comma b, then this definite integral is equal to this expression involving an indefinite integral. For the rest of this video, we'll use the fundamental theorem of calculus in examples. So the first example that we'll do is revisiting an earlier example. We want to use the fundamental theorem of calculus to find this definite integral. Now remember that that definite integral is defined to be the value of this blue shaded area, the region between the graph of little f equals 5 plus x squared over 10 from x equals 2 to x equals 12. That signed area. Previously, we used a computer to estimate that signed area. We estimated that signed area to be 107.33. Well, let's compute that definite integral using the fundamental theorem of calculus. The fundamental theorem of calculus says that this definite integral is equal to the result of doing this calculation involving the indefinite integral. Now, this tells us what we need to do. We need to find the indefinite integral first. And so I'll do that over on the right in an indefinite integral details box here. So the indefinite integral of 5 plus x squared over 10, we compute in the standard way. We use the sum and constant multiple rule to break the integral up into two integrals and pull the constant multiples out front. Then we use the power rule for indefinite integrals, and then we end up with this result. Notice in this step we have a power function with n equals 0, and in this step we have a power function with n equals 2. So when we use the power rule with n equals 0 and n equals 2, these were the results. And then we take the results of that indefinite integral and we substitute them back into those parentheses. And then we do what this symbol tells us. That is, we have to compute the change in that quantity from 2 to 12. That means that we substitute 12 in to get this expression, and we substitute 2 in to get that expression. And then we subtract. Notice that when we subtract, the plus c's cancel, and we end up with this result. That's a number. Notice again that the result of the indefinite integral is a function form. There's a constant of integration, a plus c. There's a plus c here, there's a plus c here, there's a plus c here. Those plus c's cancel, and you end up with a result that does not have a constant of integration. It's just a number. 322 over 3. Written as a repeating decimal, that would be 107.333 with a bar over it. That's an exact answer. Hey, our previous approximation for this was 107.33. We estimated that based on those computer results. So that previous approximation was pretty good. Let's go on. For our next example, we are supposed to use the fundamental theorem of calculus to find this definite integral. Well, we'll use the same format that I used in that example. There's our result. Now, notice that the instructions were to give an answer that is an integer or a simplified fraction. So that's this answer. The number 7/6 is the exact answer. If you type this into a calculator, then what you end up with is not an exact answer. So what the question is asking for is this. So keep in mind, again, that if you get a decimal from a calculator, it's generally not the exact answer. So if the question is to give an answer that's an integer or a simplified fraction, this is the form. Notice the details of this calculation. Again, we use the fundamental theorem of calculus to enable us to compute this definite integral by doing this calculation involving the indefinite integral. I did the indefinite integral details in this box off to the side. The indefinite integral calculation involved the standard stuff, rewriting the integrand in power function form, using the constant multiple rule, recognizing that we had a power function with n equals -2, so we could use the power rule, and in the end, rewriting the final answer in positive exponent form. Then taking that result and substituting it back into the expression for computing the definite integral. Notice again that the result of the indefinite integral was this function form that has a constant of integration, a plus c. That plus c shows up there, but the plus c disappears soon after. It gets canceled in this subtraction step. Lots of steps here. No one step is all that hard, but you can see it's a whole page of math. Example 6. Use the fundamental theorem of calculus to find this definite integral. Well, we do the same approach. We write down the definite integral that we want to compute. The fundamental theorem of calculus tells us that we can find that definite integral by doing this computation involving the indefinite integral. Then I do the indefinite integral details off to the side. So that indefinite integral that I need, I compute in these steps off to the side. Then I substitute that back in to those parentheses. Notice that the indefinite integral is a 1 over x type integral. So I pull out the constant multiple of 3, but I do not write the integrand as a power function. I leave the integrand as 1 over x, and then I use the indefinite integral rule for 1 over x and I end up with this expression, 3 ln of absolute value of x plus c. A couple of things to notice here. There is this plus c, the constant of integration, which we know is going to disappear soon after when we do the subtraction. The other thing, though, that's annoying is this ln of absolute value of x. We have absolute values in our answer. But that's okay. We'll see that they disappear soon as well. So we substitute the result of this indefinite integral into the parentheses, and then we have to find the change in that expression from 2 to 10. So that just means that we substitute in 10, and we substitute in 2, and we subtract. Then we get to work simplifying. Again, the plus c's cancel right away. But also, look at this. Absolute value of 10, we know, is just 10. And absolute value of 2 is just 2. So those symbols get simplified quite a bit. Also, remember the rule of logarithms. ln of a minus ln of b is ln of b over a. So we use that rule to simplify that logarithm expression, which simplifies further to 3 ln of 5. So there is an exact answer. A decimal approximation rounded to 3 decimals would be this. So the only way to write that answer exactly is 3 ln of 5. Doesn't matter how many decimal digits you write down, it won't be exact. So it's useful to know how to write the exact answer in symbols, and it's also useful to be able to type that into a calculator or computer and get a decimal approximation so that you have an idea of how big that number is. Example 7. Use the fundamental theorem of calculus to find this definite integral. Well, we'll use the exact same form. We write down the definite integral that we want to do, and then we use the fundamental theorem of calculus to show that we can find that definite integral by doing a computation involving the indefinite integral. There's our result. We used the same approach. We started by using the fundamental theorem of calculus to replace this definite integral with this expression involving the indefinite integral. We did the indefinite integral details off to the side, substituted them back into the parentheses where the indefinite integral was sitting. The steps in the indefinite integral were the standard ones. We rewrote the integrand first into power function form. We used the constant multiple rule to pull that constant multiple out front. We used the power rule, knowing that n was 1/5. And then I carefully rewrote the result, trying to do just one arithmetic step on each line, being careful, noting that 1/5 plus 1 is 6/5, and then noting that dividing by 6/5 is the same as multiplying by 5/6, and so forth. The constant of integration is in the indefinite integral result. It shows up here, but then it gets canceled soon after. And then the calculation simplifies quite a bit, because when you substitute in x equals 0 and x equals 1 into this expression, the results are very easy to simplify. You end up with just this fraction, 25/6. That is a simplified fraction. The instructions were to give an answer that's an integer or a simplified fraction. The instructions don't call for a decimal, so this is the answer. Let's go on. Example 8. Use the fundamental theorem of calculus to find this definite integral. I'll use the same format. And there's our result. Notice that we use this indefinite integral rule for the indefinite integral of e to the kx. It's useful to always think of the pair of rules. The derivative rule is that the derivative of e to the kx is k e to the kx. But the indefinite integral rule is different. The indefinite integral of e to the kx is e to the kx over k plus c. Notice that the instructions were to give an exact answer and a decimal approximation rounded to 3 decimal places. I got all the way to the exact answer. This is the way to write the answer in symbols. E to the 6 minus 1, that whole quantity over 3. Then that whole expression can be typed into a calculator to get this decimal approximation rounded to 3 decimal places. Let's go on. Example 9. Use the fundamental theorem of calculus to find this definite integral. Well, that's very similar to the definite integral that we've already done. We found this definite integral, the integral of 5 plus x squared over 10 from 2 to 12. And we got this result, 322 over 3, which can be written as a repeating decimal, 107.333 with bar over it. So why are we being asked to do this integral again? Well, we're not being asked to do it again. Notice that the limits of integration, the lower limit and the upper limit, have been reversed. Instead of integrating from 2 to 12, we're integrating from 12 to 2. So we don't have to go through all the gory details of the integration again. We just have to use the properties of definite integrals. So we use the result of example 4 to say that this indefinite integral is this number. We just have the minus sign in front of it for the current example. Let's go on. There's one more example. Example number 10. Use the fundamental theorem of calculus to find this definite integral. Now that looks awful. Notice how messy the integrand is. We don't have any indefinite integral techniques that would let us integrate something that messy. But remember, we've actually seen this problem before, even before we learned about the fundamental theorem of calculus. The key is to note that the lower limit and the upper limit of integration are the same. So this is kind of a trick question. We don't really need the fundamental theorem of calculus. So the result is that this definite integral is just the number 0. We don't need the fundamental theorem of calculus. And again, we don't have the techniques to find the indefinite integral that we would need to do using the fundamental theorem of calculus. So it's a good thing. Well, that's the end of that example, and that's the end of the video. Thank you.